Your voice is a wave, your heartbeat is an electrical pulse. The Wi-Fi delivering this video to your screen, a radio wave rippling through the air right now. These feel like completely different things. They're not. They're all signals, and that word, signal, is more powerful than it sounds. A signal is any quantity that changes and carries information. That's the whole definition. Your voice, a heartbeat, a stock price chart, the brightness of pixels on your screen updating 60 times a second, all signals. But signals don't just exist in isolation, they move through things, they get transformed. Your voice enters a microphone, out comes a voltage, that voltage enters a codec, out comes a compressed data stream, that stream reaches a speaker on the other side of the world, and what comes out is sound again. Something is always acting on the signal, that something is called a system. A system takes a signal in and produces a signal out. The box can be a microphone, an amplifier, a noise-cancelling algorithm, the human inner ear. It doesn't matter what's physically inside, they all do the same abstract thing: input, transformation, output. And the reason we draw a box with a question mark, the reason we abstract it this way, is so we can study all of them with the same tools. Here's the question that actually matters: how do you understand what's inside that box? Not for one specific input, for any input. A filter doesn't just handle one sound, it has a rule it applies to every possible sound. A communication channel doesn't carry just one signal, it carries everything you throw at it. To truly understand a system, you have to ask what it does to every possible signal. Once you ask that question, the system stops being a mystery. Its behavior across all inputs is the system. Two completely different devices, one built from copper wire, one written in Python, can be mathematically identical if they transform every signal the same way. The box doesn't matter, the behavior does. Now, signals come in two forms, and which form you're working with changes the mathematics. A continuous time signal, written x of t, has a value at every single instant, smooth and unbroken, a vinyl record, an analog radio wave. A discrete time signal, written x of n, has values only at specific moments, snapshots taken at regular intervals, a digital audio file, a sensor reading once per millisecond. Parentheses and square brackets are not interchangeable. Parentheses mean every instant of real time, square brackets mean integer sample points, same information, different mathematics. This distinction matters because the physical world is continuous, but every device that computes anything works in discrete samples. You need both. Now here's where it gets useful. Most real-world systems, amplifiers, filters, communication channels, share two simple properties: they're linear, and they're time invariant. When both are true, we call it an LTI system. And when a system is LTI, the mathematics becomes clean, solvable, elegant. You can know exactly how it will respond to any signal, using one unified framework. That framework, convolution, the Fourier transform, the Laplace transform, filters, all of it flows from just those two properties, and that will be covered in the next videos. Think about what's happening right now. This video traveled from a server to your device as a compressed signal. Your device decoded it, a system. Your screen displayed it, another system. Your speakers converted electrical signals back into sound, another system. So why does it matter? Every MRI image ever taken, the raw data from the scanner is literally the Fourier transform of the image of your body, and the picture a doctor sees is the mathematical inverse of that data, computed automatically, a mathematical operation running silently beneath medicine. Your noise-cancelling headphones are listening to the incoming noise and generating an exact mirror of it, a system designed to invert a signal so completely that the two cancel each other into silence. These aren't just examples, they are the reason we study signals and systems, because the same mathematics that describes a heartbeat also describes a radio wave, a financial market, and the human ear, and once you have the language, everything connects. This is not a narrow technical subject. Signals and systems is the hidden architecture of almost everything that processes information in the modern world. You've always lived inside it. Now you can see it.